Okay, so today we will be starting linear algebra, and for this you already have the access to this book, Linear Algebra with Applications. So if you click it, then
it opened in other page.
Yeah, it's open in other page.
It's in the other tab, like, yes, that's one.
Can you see now? Yeah. Okay.
Yes.
Yeah. So so in this book you have several chapters. So we will cover, I think, many of those chapters, maybe at least up to chapter number 11. But we will not cover everything. For example, in each chapter, there will be some topics with these asterisks. These are the yeah. For example, this topic is with asterisk, and the other one is also, and then similarly in other chapters. So because of the time limitations, we will not cover those topics with asterisks. These are some optional topics. Only the necessary and essential topics we will consider. So today we will start from chapter number 1, systems of linear equations. Okay, I would strongly recommend to follow this book, as this book has many examples, and then also at the end of each section. So for example, in chapter 1 there are section 1.1 and section 1.2 and then other sections. At the end of each section, if you will see, you will not only there are examples over here, many examples over here, and then there are some practice problems which has also been given over here, practice problems. So the practice problems, the solutions of these practice problems you can find at the end of the book as well. And then of course there are some exercises. So this book is in this sense is quite very useful because it has so many examples given, and then you can practice quite a lot from this book. So the solutions of the practice problems are over here, the solutions of practice problems, and then the answers of the selected exercises. Okay, so our topic today is the systems of linear equations. Actually, I will rather go very quick in this topic, because this is the system of linear equations for which I think most of you will be somewhat familiar. The only thing will be that we will be solving these systems of linear equations in a more methodological fashion. I will not go into the theory very much. I will just solve some examples, and with the solution of those examples, you can understand the theory. You can, for the theory, you can also look at the book, and then also lecture slides of this, of the two topics, which lecture slides of the topics I have already uploaded on the Moodle. Okay, so let's start from the one of the example right at the beginning. Oh, okay, wait a minute. I need to connect my. By the way, can you hear me?
Yes.
Okay.
Yes, we can totally hear you.
Okay, so yeah, so now my pen is working. Yeah, okay, here. So our topic is chapter 1. Okay, chapter 1 from the book. The author of the book is Jeffrey Holt. Okay, by Holt book. Okay. So the chapter 1 is a system of sorry, what happened? What's happening over here? A system of linear equations. Give me a minute. I need to adjust something because in my display something is not very good actually. Okay, so let's, as I have just told that I will just present some of the examples. So let's say as an example, let's take this example. So I present you two equations. So one equation is 14x1 plus 5x2 is equal to 13. And then 6x1 plus 2x2 is equal to 8. And verify that 7 minus 17 is the solution. So this is the very basic example we can start from. So for the verification, we will just put the values of x1 and x2. So this will be the x1, and this will be the x2. So x1 will be 7, x2 will be minus 17. So if we will put these values, 14 into 7 plus 5 into minus 17, so that will be equal to 13. So 14 into 7 is 7 4s are 8, and then 98 minus 85 is equal to 13. So 98 minus 85, 13 is equal to 13. So first equation is satisfied. The second one is 6 into 7 plus 2 into minus 17 is equal to 8. So 42 minus 34 is equal to 8. 42 minus 34, 8 is equal to 8. So this is like a very school level stuff which we have done. Okay. Let's take another one. Okay, so this will be something a little bit different. 3x1 plus 5x2 plus 7x3 is equal to 14. 2x1 and then plus 4x3 is equal to 4. And then we have to verify it for this minus 14 plus 10 s1 s1 and then 8 minus 5 s1. So we want to verify that this is the solution. So this will be x1, this will be x2, this will be x3. Here I can say, as I have said, that this will be a little bit different because you see that we have 3 unknowns, as we know from our previous knowledge. X1, X2, and X3 are 3 unknowns. This is a linear equation, and then this is a second linear equation. So 3 unknowns, but 2 equations only are available over here. So in this case, we still are talking about the solution. So in generally, without the theory, without looking at the theory of the linear equations, we will simply not bother to solve this equation. We will say that, no, okay, we cannot do that because it will not provide you any solution. But in reality, it is not true. In reality, it is said, the theory will say that in this case, we will have unlimited solutions in the form of this S1. So S1 will be a kind of, S1 will be a free parameter. Okay, it will be called as a free parameter. So in this free parameter, which can take any value, okay, any real value, in this free parameter, we can represent its solution. So this we can also verify it. So for example, in this case, we will replace x1 x1 with minus 14 plus 10s1 plus 10s1, and x2 will be replaced by s1, and then x3 will be replaced by 8 minus 5 s1. and that should be equal to 14. So we can verify it. 14 times 3 is minus 42 plus 30 S1 plus 5 S1 plus 56 minus 35 S1 is equal to 14. So 30 S1 plus 35, so minus 30. So S1, S1, S1 are cancelled. For 56 minus 42, 14 is equal to 14. So indeed, this is a solution of this. But the difference is that S1 can take any value, any real value. So because it is a free parameter. So this is something which we will learn new uh, uh, in this course. And then for the second one, so 2x1, 2 into minus 14 plus 10s1, and then plus 4x3, x3 is 8 minus 5s1. So that is equal to 4. So indeed, it should be 20 minus 28 plus 20s1 plus 32 minus 20s1 is equal to 4. So minus 28 plus 4, 32 is 4, minus 20s1 and minus 20s1 cancel. So 4 is equal to 4. So indeed, this is the solution of this kind of equation. Okay. So this is one step which we can find in this solution, in this topic. Okay, so let's look at one more example. If we have a system of equations like this, as I'm going to write now, 2x1 minus 2x2 plus 3x2 is equal to 3. And then the second solution is 3x2 plus 2x3 is equal to 21. And the third equation is 5x3 is equal to 15. So you can see that we have now 3 equations, 1, 2, 3, 3 variables, x1, x2, and x3. But the thing is that in the first equation, we have all the 3 variables. In the second is that we have one less variable. And in the third one, we have even one less variable. And you can see that the first variable, which is called as the leading variable in each equation, is one step further in the previous equation. Okay, so for example, the leading variable in first equation is x1, the leading equation variable in second equation is x2, and then say leading variable in third equation is x3. So and then in the second and the third equations, the leading equation of the first equation and the second equations are not present. So such a form of the equation, is called as the triangular form. So the exact definition of the triangular form is given in the book, but in simple words, if you want to explain it, you can say that the triangular form is the one in which you have the leading variables are different in each equations, and then the one of the leading variables and the previous case is not present in the next equation. So this is the triangular form of the equation. So this triangular form of the equation is useful for the solution purposes because we can use the back substitution method to find the solution of the problem. So by the back substitution, we can start from the last equation. So the last equation will now give the value of x3 is equal to 15 by 5, which will be equal to 3. And then this value of x3 will be back substitution into the previous equation. So it will be 3x2 plus 2 into 3 is equal to 21. So which will give us the value of x2 will be equal to 21 minus 6. It will be 15 by 3 is 5. So x2 will be equal to 5. And then using these two values, we will back substitute into the first equation. So 2x1 minus 2 into 5 plus 3 into 3 is equal to 3. So we can solve it. So for example, 3 minus 9 is minus 6. Minus 6 plus 10 is 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 4. 4 divided by 2 is 2. So x1 will be 2. So we will find the solution set x1, x2, x3 will be like 2, 5, and 3. So we will find 2, 5, and 3 as the solution. So in this case, as you can see that in the back substitution, it gives us a great advantage of finding the solution rather very quickly. Well, you can say that, okay, why should we care about this triangular solution? Now we have easily find these solutions by, for example, even Microsoft Excel, we can use matrices and these sort of things. The thing is that we need to use this kind of methods to understand the process behind, and even the even the computer methods use these kinds of forms of the solutions to reduce the amount of computation. So just consider that if we have something like thousands of equations in more practical cases, it becomes very time consuming even for the computers to arrive at the solution. So it will be more efficient for the computers even to use these kind of algorithms to find the solutions. Okay. Okay, let's look at one more example. Yeah, in this example, we have the equation like this. So 6x1 plus x2 minus 3x4 is equal to 11. And then 3x2 minus 4x3 plus 5x4 is equal to 6. And then 2x3 minus x4 is equal to minus 3. So in this case, you have how many equations? 3 equations. But you have how many variables? 4 variables. Okay, so we have 3 equations and 4 variables. So, but the form of this equation, but the form of this equation is a triangular. So you can see that in the first equations, the leading variable is x1. In the second equation, the leading variable is x2, and then x1 is not present. In the third equation, the leading variable is x3, and then x2 and x1 are not present. In fact, we don't have any other equation. Okay, so in this case, what we can do, we can find, since we have more variables than the number of equations, so the solution will not be unique. So solution we can find in terms of some a free variable, okay, in the form of some free variable. So what we can say over here is that if we want to complete this solution, okay, this equation, so what we can say is that so for example, x1, x2, and x3 and x4, and then it should be x2, x3, and x4, and it is x3 and x4, and the last equation should be equal to x1. It should, if we want to complete its triangular form, okay, so the last equation should have x4, something like this. So we assume that the value of x4 is equal to S1 in this case. So where S1 is a free parameter which can change values. So in this case, if we take x1 is equal to x4 is equal to s4, so then we can find the values of x3, x2, and x1 in terms of this parameter. So this we will assume, and then we can find that 2x3 minus 4s1 is equal to minus 3. So this will give x3 is equal to, x3 will be equal to then minus 3 by 2, minus 3 by 2 plus 4s1 divided by 2, it will be plus 2s1, okay, the value of s2. So this value of x2 will be back substituted into this equation. So it will be 3, sorry, this will be the value of
x3.
x3, yes. Okay, this will be the value of x3. And Next, we can back substitute this value of x3 and x4 into this equation. So it will be 3x2 minus 4x3. So 4x3. So 4x3 will be minus 3 by 2 plus 2s1. Okay. And then plus 5x4, 5s1, that will be equal to 6. Okay, so after some algebra, then you can find that the value of x2 will be equal to 4 plus s1. Okay, I'm not going these calculations, but definitely you will find this value 4 plus s1. And then in the first equation, then 6x1 plus 4 plus s1, x2 value minus 3x4, x4 is s1. So that is easy. So 6x1 will be equal to 11 minus 4, that is 7. Yeah, so 11 minus 4, that is 7. And then it will be 3s minus s1. So that will be plus 2s1. So x1 will be equal to 7 by 6 plus 1 by 3 s1. Okay, 7 by 6.
Sorry, Professor. I have a question. So in the first example, why did we multiply 3 to 3 when we found x1 equals to 2?
In first example?
Yeah, in the first example. Because we have to multiply 3 to x2.
Here?
No. There, above, in the first equation.
In the first equation?
Yeah, 2x1 minus 2x2 plus 3x2 equals 3, isn't it?
2x1 minus 2x2, yeah.
Plus 3x2.
Yes, is equal.
And then when we put the numbers.
Sorry, it's 3x3, sorry.
It's 3x3. Oh, okay.
So yeah, some typing mistake. Okay, so so that was the example. So the solution set is, so we can write the solution set like this as well: x1, x2, x3, x4. So whatever form you want to find in the row form or column form, you can write the solution set like this. So the solution set will be, so the first one will be this one, 7 by 6 plus 1 by 3 s1. The second one is 4 plus s1, 4 plus s1. And then we found minus 2 by 3. Okay. Then we found minus 3 by 2 plus 2s2, minus 3 by 2 plus 2s2. Oh, and I have left out the space. So then the last one is s1. Okay. Anyway, you understand it. Okay, so this is one of the examples. Next, we have one more example. So in this case, we have x1 plus 3x2, and then x3 is missing. Then we have 3x4 minus 5x5 is equal to 5. And then in the second equation, we have x3 is missing. x2 and x1 and x2 are missing. So we have x3 minus 6x4 plus 10x5 is equal to minus 7. And then in the third equation, we have x1, x2, and x3 are missing. 3x4 minus 5x5 is equal to 6. So in this case, we have 3 equations, but 5 variables. So when we have 3 equations and 5 variables, so we have 2 less equations. So therefore, we need at least 2 variables. Okay, 2 variables in this case. So in this case, we can assume that, for example, we can assume that which variables are actually we can assume. Okay. So for example, what we can do is we can assume x1, x5 is equal to, I think maybe we can assume x5 is equal to s1. Okay, so that we can apply the back substitution method, because this equation is in the you can say that it is in the triangular format, but it is not a complete format. So it will be better if we assume x5 is equal to s1 and then find the values of x4 and like that in terms of the other variables. So if assume x5 is equal to s1, then what will be the value of x4? So x4 from the last equation, 3x4 minus 4s1 is equal to 6. So from here, x4 will be equal to 6 divided by 3, 6 plus 4 s1 divided by 3. So it will be 2 plus, sorry, 3, no, 3 times 2, oh yeah. So it will be so 6 plus 6 divided by 3 is 2, 2 plus 4 by 3 s1. Okay, so it will be 2 plus 4 by 3 s1. And now in the previous equation, now we have x5 and x4, right? In the previous equation, we have x5 and so we have to find the value. We have now know the values of x5 and x4, and then from the application of this previous equation, now we can find the value of x3. Okay, because we know these values. So x3 minus 6 x4 is 6 times 2 into 4 by 3 s1, and minus 10 x5 was s1 is equal to minus 7. So from here we can find the value of x3. How can we find? We need to make some algebra. Minus 12, and then it will be minus 8 s1, and minus 10 s1 is equal to minus 3. So x3 will be equal to 12 goes there, so it will be 5, and then it will be 5 plus 18 s1. Okay, so now we know the values of x3 as well. So now in this first equation, now we only have to deal this first with this first equation. Actually, we now know the values of x3. Okay, we know the values of x3, x4, x5. But in this first equation, now we have two unknowns, x1 and x2. So we have no other choice rather to assume the value of x2 to be another free parameter. Okay, so in this case, what we will do is x1, and then we will assume that if we want to find the value of x1, or maybe we can choose the value of x1 to be s1, or it's our choice. Okay, so x1 and plus 3 x2 we will assume equal to s2. Okay, any free parameter. And now we can because there is no x3, so we will put 3 into x4. X4 is 2 plus 4 by 3 s1, and minus 5 x5 is s1. Okay, so now we can find the value of x1 in terms of s2 and s1. I will not do it over here, but you can just find the value of x1. So therefore, our solution set over here will be x1, x2, x3, x4. So whatever values we have found, in this case, what we have found over here is the value of x1 will be in terms of s2 and s1. The value of x2 was actually s2. The value of x3 was in terms of s1. The value in terms of s1, and the value of x4 and x5 are also in terms of S1. The value of x5 was itself actually x5. So in this case, whatever the value you will find, you can input over here and then it will complete the solution. So remember that the solution in this case and in the previous case will not be unique. Even if you choose something like x1 is equal to s2 or x2 is equal to s1, so the form of the solution will be different because there will be no unique solution in this case. So only the way which we are going to present over here that will matter most. Okay, any questions up to now?
Professor, excuse me, could you please tell me on the right side, the first equation, so it is equal to 0?
First, for example, this first equation?
No, on the right side.
Here, x5
Lower.
is equal to s1.
No. x1 plus 3s2 plus 3.
Here?
Yeah. Yes.
Is equal to 5.
5. Okay, thank you.
I mean, without in the flow of that, I can sometimes make mistake, but it's good that you have pointed out. And then I think I just have left it for you to solve. Okay, solve. Okay, and then you can find the solution in terms of some function of S1 and S2. Okay. Okay.
Excuse me.
Yes.
Question.
Yeah.
I a little bit missed this moment. Like in the beginning, x1 plus 3x2 plus, is it plus 3x4 or plus x3 minus x? Well,
yeah, x3 is missing over. X3 is not present over here, so that's it. So yeah, in order to write in some alignment, I just put a space over here. Other than nothing, because x3 it actually is 0 x3. You can say
okay.
0 x3. Okay, so yeah, let's take one more example. This example talks about the consistent or inconsistent solutions. Okay, so consistent equations. Okay, consistent versus inconsistent equations. Okay, a system of equations, equation systems. Okay, what is the inconsistent system? The inconsistent system is like that. So for example, if you have, we are talking about the linear system. So the linear systems of the equations, for example, in two variables, we can represent in the form of lines. Okay. So for example, if I say that the equation is something like a1 x1 plus a2 x2 is equal to b, okay, and then the second equation is a2 x1 plus a3 x1 plus a4 x2 is equal to c. So these are the two equations of lines. Okay, you remember that the equation of line is represented by y is equal to mx plus c, where m is the slope, or this is the equation of the line. So when we have these two, some of these equations, and if we see that these two lines are parallel, for example, if this equation represents this line, and if this equation represents this line, these two lines are parallel. Okay. So if these two lines are parallel, these two lines are will not be intersecting with each other. Okay. Although nothing will be wrong with these lines but since these two lines are not intersecting with each other, they will not produce any solution. Okay, so parallel lines do not produce any solutions. So if we have a system, if we have such a system in which we have those parallel lines, then we call such a system as a inconsistent system. And that inconsistent system has no solution. So the inconsistent system has no solution. Okay, example. Okay, example is, for example, if we have 6x1 minus 10x2 is equal to 0. This is one line. And the other equation is minus 3x1 plus 5x2 is equal to 8. If we try to solve these two equations, so what we can do is we can multiply the second equation by 2 and then add to the first equation. So I rewrite the first equation, 6x1 minus 10x2 . 6x1 minus 10x2 is the same as is equal to 0. And now I multiply this equation by 2 and then add to the first equation. So it will be minus 6x1 plus 10x2 is equal to 16. And now I will add these two equations over here. So x1 will eliminate, okay? And then minus 10x2 plus 10x2, they will also eliminate. So I will get 0 is equal to 16. So now can you say that 0 is equal to 16, which is false, okay? So we cannot have 0 is equal to 16. So if by doing these row operations, we get an impossible result, okay? If we get an impossible result, then we will say that the system of equations is inconsistent, okay? Systems of equation is inconsistent. So if the system of equation is, if we don't get this type of result by the row operations in the equations, then we say that the systems of equation is consistent, okay? So the consistent system will have either one solution or infinite solutions. Okay, there are only three possibilities. So that means if we have a system of linear equations, one equation, second equation, third equation, n equations, so we can have either of these three situations. Either this solution system of equations will have no solution, okay? So in that case, that system of equations will be inconsistent. Or if the system of equations is consistent, then we have two more possibilities. It will have either one solution or infinite solution, nothing in between, okay? Okay, so in the previous case, when we did those examples in which we used the free parameter, so the system of solutions was having infinite solutions. So in the infinite case, what we get actually is, for two dimensionals, we get two lines, okay, which are actually same, lines. So for example, if we have for example, an equation something like 2x1 plus 3x2 is equal to 5, okay? And another equation we get like 5x1 plus 5x1 plus into plus 3 times 3.5. 7x2 is equal to 7.5. Okay, you can see that clearly the second equation is 2.5 times the first equation. Okay, so basically both equations are same. Okay, so if for example, if I multiply this by 2.5, this second equation, and then subtract one equation from the other equation, I will get a situation which will be 0 is equal to 0. 0 is equal to 0. So in this case, when we get this situation, when 0 is equal to 0, instead of 0 is equal to 16 or 0 is equal to some other number, we will not say that this system is inconsistent. We will say that the system is inconsistent, but it will have an infinite solutions, many solutions, infinite number of solutions. So in this case, both the lines are the same. Okay, both the lines are the same. And when we, in the case of the one solution, then that means both lines will be intersecting, and then you can see that intersecting lines can only intersect at only one point, and that intersecting point will be the solution. Okay, will be the solution. Remember that I have just given the examples of the lines, and the lines have only two parameters, x1 and x2, or in that case x and y. The same can be true for 3 parameters that we can show as the form of a plane. Okay, so same will be show for more than 3 parameters, but more than 3 parameters we cannot show on paper. I think we cannot even visualize it as well. But it is from the conceptual point of view, more than 3 parameters, x1, x2, x3, x4, x5, x6 will also follow the same rule. So it means that it is a theorem in this in the theory of linear equations, is that a system of linear equations, a system of linear equations will either have no solution or one solution or infinite number of solutions. Okay, number of solutions. So this is the theorem. Okay, anyway, we don't need to prove this theorem. It may be too time consuming. Okay, so with this, let's take do one example. Oh, we are almost to the end of this lesson. Okay, so suppose that we have 2 sets of equations. Okay, example. Okay. This is the example about the inconsistent as well as inconsistent systems. Example. So 5x1 plus x2 is equal to 7. And another system is 2x1 plus kx2 is equal to 2. So the question is, for what value of k the system will be inconsistent. System will be inconsistent. So for example, I think we can solve these 2 equations because the value of k is unknown. So we can find its solution very easily in terms of the value of k. But for this system to become inconsistent, a k should have some particular value. Okay, so if k will have some particular value for which it will become inconsistent, so what we can do is we should have some impossible situation over here. So it means that for the inconsistent case, what you can assume, what you can observe is that the left-hand side of the equations should be the same. Okay, left-hand side of the equation should be the same. So in this case, what we can do is, what I can multiply the second equation by, say, 5/2. Okay, so that I can eliminate x1. Okay, so if I can eliminate x1, then 5x1 plus x2 is equal to 7. And then if I multiply it by this, so it will be 5x1 plus 5/2 kx2 is equal to, that will be 5. Okay, and now let's say it is minus, so it will be minus, and let's say I multiply by minus 5/2. So it will be minus, and then it will be minus. So now I add them together. So what I get is, 1 minus 5/2 kx2 is equal to 2. So for inconsistent form, I should have this type of situation: 0 is equal to c. Okay, so if this has to be inconsistent, so this side should be equal to 0. So it means 1 minus 5/2. Sorry, I made it very messy over here. Okay, let me write it again. Okay, so it will be 1 minus 5/2 k times x2 is equal to 4. So this 1 minus 5/2 k should be equal to 0. So from here I can find that the value of k should be equal to 2/5. Okay, so the value of k is equal to 2/5 will make this system of equation inconsistent. For any other value of k, the system of this equation will be consistent. Okay, is it clear? Hello? Any questions?
I guess no questions.
Okay.
Yeah, no questions.
Okay, so so in today's lecture, I covered section 1.1 of chapter 1. Actually, I plan to cover section 1.2 as well, but in the end, I found that I did not have enough time. So we will then cover section 1.2 in the next lecture. Okay. Okay, that's all for today. So.
Thank you. Goodbye.
Thank you.
Goodbye.
Bye-bye.
Thank you.
Bye-bye.
Thank you. Goodbye.
Goodbye.
Bye-bye.
Thank you. Goodbye.
Bye-bye.